Everybody wanted to make a very short video of re-emphasizing the validity issue of reverse causality or simultaneous causality. So we'll just go through it very quickly so that you take another look at it in the textbook and look at it a little more carefully. And we can see the main result, which is that simultaneous causality results in there being a correlation between the error term, so epsilon I or mu I, right? However you want to write the error term, epsilon I or mu I. There'll be a correlation between the error term and the x, and that's a violation of our assumption that we make in econometrics, right? Which is that we'll have an unbiased estimate of the coefficient if the expected value of the error term conditional on the x is equal to 0. And that condition will be violated when we have this condition that the expected value of the error term conditional on the x is equal to 0 will be violated when the error term is correlated with the x. Remember, the error terms, other factors, measurement error. So let's go ahead and see the simple intuition of why that's the case. So we imagine we have two equations. Equation 1 says that yi equals beta 0 plus beta 1 xi plus mu I, an error term. So mu I is the first error. And equation 2 says that xi depends on yi. So xi equals gamma 0 plus gamma 1 yi plus vi. The error term here is v. And we can assume that mu and v are totally uncorrelated, but now we'll see how mu, this error, could be epsilon, right, will be correlated with x. And the reason, the intuition is very simple. If mu I is high, then the y outcome will be high. If gamma 1 is greater than 0, then xi will be high. So mu I high means yi high, yi high means xi high. So therefore, mu and xi are correlated. When mu I is high, xi is high. So very straightforward intuition here of how, if we have simultaneous equations, and remember, in economics, we have simultaneous equations all the time. Price causes quantity, quantity causes price. They're simultaneously determined. Income causes consumption, consumption causes income, simultaneously determined. So in economics, we have all kinds of simultaneous equations going on. So we would expect this, what's sometimes called reverse causality or endogeneity or simultaneity, to be pretty common in economics. We can take a look here a little bit at the proof of that was a little bit of intuition, but let's take a look. It's a good chance to see the covariance operator in action. So we have the covariance of xi and the error term, and because xi is defined here, we can substitute it in. So that's the covariance between gamma 0 plus gamma 1 yi plus vi and mu I, the error term. So remember that the covariance of a sum of terms with another term is equal to the sum of the covariances. Now, the covariance of gamma 0 with mu I is just 0 because gamma 0 doesn't vary. So we have the covariance of, and we can bring the gamma 1 out. So our first term is gamma 1 times the covariance of yi and mu I. And then here we have the covariance of vi, mu I, the two independent error terms and the two separate equations, which just for convenience we'll assume is equal to 0. So we're left with this. The covariance of x and mu is equal to gamma 1 times the covariance of yi mu I. But now we can do the same thing again. Yi is by definition equal to this. So now we substitute that into the first part of the covariance term. So the covariance of this sum with mu I is equal to the sum of the covariances. They're all multiplied by gamma 1. So now we have the covariance of xi mu I is equal to gamma 1 times beta 1 times the covariance of xi mu I, plus gamma 1, the variance of mu, which is expressed as sigma, because the covariance of mu I with mu I, the covariance of a random variable with itself is just the variance of that random variable. So now this equation, we have common factor covariance xi mu I, covariance xi mu I here. So we bring this over here. So it's 1 minus lambda 1 beta 1, which is what we have in the denominator here. And the point of doing all this, right? Let me erase all these drawings. The point of doing all of this is that this covariance is, since we have a variance term in the numerator here, that's always a positive number. So there's no reason this is going to be equal to 0. So if we have simultaneous causality, as we do here, we just showed that the covariance of xi mu I will not be equal to 0. So the expected value of the error term will not be equal to 0, conditional on the x, and our estimated coefficient will be biased. I haven't talked about how do we solve that problem. For that, we need to go to the next level in econometrics next course, solving, estimating simultaneous equations. It's totally solvable. It's not a huge problem in econometrics, but we don't have the tools right now to address that. So for now, all we're doing is showing that it would be biased.